I want to thank Google's Science Journal app for supporting PBS Digital Studios.
Black holes. They're weird. And a recent paper about them seems to me to be the strangest one yet. Black holes might be covered in hair. I'm Diana, you're watching Physics Girl, and it's been a while since I made a YouTube video, so I hope you're ready for me to get excited about space stuff. Let's get started. So, iconic theoretical physicist Stephen Hawking may have passed away in 2018, but papers he wrote are still coming out after his death. His latest paper, released in October, argues that black holes might be covered in soft hair. What does he mean by that? We're gonna get there by the end of this video, but first we're gonna understand what the heck a black hole is by doing a cool, weird demo that shows us intuitively why you cannot escape a black hole. According to Einstein's theory of relativity, the gravity of any given object is proportional to its density. So if an object is dense enough, then nothing that gets too close can ever escape, no matter what. Nothing, not even light, can escape from an ultra-dense object, so we would call that a black hole. Also, can we just take a moment to admire this black hole? My incredible animator made this. This isn't stock footage, this is a Physics Girl black hole, yo. That's all. Now, from the explanation of nothing being able to escape the gravity of a black hole, you might assume that gravity is a pulling force, and you'd be in good company. Sir Isaac Newton thought the same thing back in the 1600s. He noticed that when things move, they tend to move straight, unless a force acts on them and curves their path, a force like wind or a kick from Sir Isaac Newton. Newton then noticed that gravity also curves the path of things downwards, so he concluded that gravity must be a force. Einstein thought differently. He noticed a thing with an elevator. There was a moment he realized an elevator out in space accelerating up would act the same as gravity here on Earth. Basically, there was a problem with our theory of gravity as a force. So what is gravity then? Well, Einstein wondered, what if gravity isn't a force, but the curved trajectory of a ball flying through the air is actually straight? I'm gonna have to apologize in advance because the demo I'm gonna show you broke my brain just a little bit. Pretend you live near the equator and you start walking east, trying to walk as straight as possible on your initial path. You might think that you'd keep walking parallel to the equator and never hit it, right? Well, try testing this on a globe. Try it like this. Line up the edge of a piece of paper so it's parallel with a latitude line, and then keep pushing it down straight to simulate your straight path. And it'll actually end up intersecting with the equator. What? In fact, if you draw the latitude line you started on your paper and then flatten out the paper, that path would look curved as well. So your path actually curves because while you may be walking straight, the earth you're walking on is not flat, no matter what any of those videos in the sidebar may tell you. That's what Einstein proposed, that gravity is not a force, but an object curves in a gravitational field for the exact same reason that your straight walking path ain't straight. Gravity is what happens when you're moving straight on a non-flat thing. Only in the case of gravity, that non-flat thing isn't the globe, it's space itself and time. That's right, the fabric of the universe, space-time, is curved by large masses, just like the Earth's surface is curved. So let's bring it back to black holes. See, they're inescapable. As an object gets denser and denser, the stuff moving near it will take curvier and curvier paths. And then when you get to black hole level dense, the path an object takes gets so curved, it'll never ever lead back out of the black hole. And then it's gone, forever, without a trace. Not even a thank you note. Rude. Except it's not quite true that an object is completely gone. And that's where the hair comes in. Now, unfortunately, while a big, dense, fuzzy black space object sounds adorable, Stephen Hawking was only using hair as a metaphor for the stuff that gets left behind when objects fall into a black hole. Why call it hair? Well, imagine everything in space as a bunch of Guess Who characters. It's easy to tell them apart because they have their own distinguishing features and unique hairstyles. Black holes, on the other hand, only have a few distinguishing characteristics. You may be able to guess some of them. Mass, electric charge, and angular momentum. That's how much oomph its spin has. Other than that, they're almost totally nondescript and bald. So, When unique, distinguishing objects like star stuff or Matthew McConaughey fall into a black hole, they disappear, leaving behind a slightly more massive but still perfectly bald black hole. Everything unique about those objects is seemingly gone, disappeared, poof, almost as if black holes are sucking personality out of the universe, depriving us of Matthew McConaughey's beautiful locks. But here's the thing. One of the fundamental ideas of quantum mechanics is that information cannot be destroyed. It can be changed into different forms, but it cannot be destroyed. So if black holes really are destroying distinctive information, then they are violating the fundamental laws of physics as we know them. The theory of black holes has a built-in contradiction. It's known as the black hole information paradox. So to try and resolve this paradox, in that 2018 paper, Hawking and his co-authors propose that black holes don't actually destroy the information of distinctive stuff that falls into them, but instead they propose a process where the information sticks around in the universe as photons on the boundary of the black hole, known as its event horizon. Basically, as Matthew McConaughey is falling into the black hole, he's also depositing really low energy particles onto the black hole's event horizon, leaving behind a fuzzy edge of hair on a black hole. The word soft is used to describe the low energy particles to distinguish them from hard particles, which just have more energy. Hence, a theory of black holes with soft hair. Hawking and his collaborators think that these soft hair photons may be where the universe preserves its information from the stuff that falls into a black hole. So the information is not destroyed, it just hangs out there on the edge. And that is roughly how Hawking and his collaborators think that the existence of these soft hairs could solve the information paradox. There's of course a lot of math too, which you are welcome to treat yourself to. It's tax season, you deserve a break. Now just to be clear, these questions are far from answered. Most of the research around black holes is theoretical. Remember, we've never actually even seen a black hole. We've only indirectly observed their existence. But while theories like this, the soft hair theories, could help solve the information paradox, they're not the final say. And that's how science is done, in bits and pieces that add to science as we know it, and sometimes don't. I think Stephen Hawking would be honored to know that people like you are still wrestling with his theories. I'm honored to be able to help keep his scholarship alive after his passing. So, thanks so much for watching, and happy physicsing, even on the real deep stuff.
I'd like to thank